So we can start now. Please, I'm starting.
Okay, madam. Okay, madam.
Please, I'm sorry. Let me go for my spectacles. Excuse me a minute. Hello. Hello.
Hi.
Yeah, please, I'm back. Okay, so we want to continue with the algebra and trig. Last week we started with the the definition and some small things that we needed to know in under set. So we looked at equivalent set, equal set, subset, complement set, operations on sets, looked at intersection, union, and then difference of a set. Okay, so we want to continue. Today we want to look at loss on set operation. Loss on set operation. So if we have three sets, ABC, if ABC are sets, the first law that we want to look at is the commutative law. Okay. And the commutative law says that set A union set B is the same as set B union set A. So if I have set A and then I have set B, we know what union means. So set A union set B is the same as set B union set A. Then we have the second one says that set A intersection B is the same as set B intersection set A. And we can have the proof. Okay, so we can prove the first one. So last week we said that if two sets are the same, they are equal. If two sets are equal, then it means that the set, so let's assume I have the set A and B. Let me try and write something. Okay. So last week we said that if I have a set A, which is equals to another set B, then it means that my set A is contained in B, and my set B is also contained in A. So if the set A is contained in B, and the set B is also contained in A, then it implies that my A is equal to B. So if my set A is contained in B and my B is contained in A, then it means that A is equal to B, or B is equal to A. Okay. So with this in mind, we want to look at this, the proof that A union B is equal to B union A. So with that definition, if A union B is equal to B union B A, then we want to show that A union B is contained in B union A. And and B union A is also contained in A union B. So if this is contained in this and this is contained in this, then we can conclude that A union B is equal to B union A. So let X be in A union B. We'll have a element set which is in A union B. We want to prove that that element which is A union B is also in B union A. So let X be in A union A. This implies that S is in A. So last week I told you that we use OR for union. So if X is in A union B, it means that X is in A or X is in B. Okay. So X is in A or X is in B. And if X is in A or X in B, we can write it as X is in B or X is in A. And then we know that X in B or X in A means that the union, the or here means union. So this means that X is in B union A. So since we've been able to prove that X is in A union B, and then we've ended here as X is in B union A, it means that A union B is contained in B union A. So that is the first one. Then the next one, I want to prove that X is in A, then we'll conclude that it's in A, X is in B union A, then it is in A union B. Okay, so that is the first one. So we can call this one equation star. Then we come to the next one. We also want to show that X is in B union A. This implies that X is in B or X is in A. This also implies that X is in A or X is in B. And we can rewrite this as X is in A union B. Then we conclude that A union B is contained in B union A is contained in X A union B. And since we've been able to show that this A union B is contained in B union A, and then B union A is also contained in A union B, then we conclude that A union B is equal to B union A. Please, are you okay?
Yes,
Hello?
madam.
Okay. Then let's continue. So that is one. You can do same for the intersection. You prove that, so the intersection too, you just prove that okay, so the intersection, we know that A intersection B is equal to B intersection A. So we want to prove that A intersection B is contained in B intersection A, and B intersection A is also contained in A intersection B. So with this, you can choose an element X in A intersection B. And then you can write this as X is in A and X is in B. And this is the same as X is in B and X is in A. Okay, it's the same. So if X is in this and X is in B, then we can write this as X is in B intersection A. So we've been able to prove the first part, that X is in A intersection B, and then X is in B intersection A. So this implies that A intersection B is contained in B intersection A. So this is the first equation. Then you can look at the second equation where B, so also want to look at B intersection A is contained in A intersection B. So you can still choose the element X, which is in B intersection A. Then you prove, you take your time, you go through this same step to conclude that X is in A intersection B. So please, there's a jump here. To prove that X is in B intersection A. And then you conclude that B intersection A is also contained in A intersection B. Then you call this one equation 2. Then from equation 2 and then equation 1 and 2, then you conclude that this is equal to this. A intersection B is equal to B intersection A. Are you okay?
Yes, madam.
Okay, let's continue. So the next law that we want to look at is the associative law. That says that A intersection B in a bracket intersection C is the same as this is union, is the same as A union into bracket B union C. Then when we come to the intersection, A intersection B in a bracket intersection C is the same as A intersection, and then you open a bracket B intersection C. Okay, so this one too, we will look at one of the proofs. So the first one, so as I did earlier, if A intersection B in a bracket intersection C is the same as A intersection in a bracket B intersection C, then want to prove that the left-hand side is contained in the right-hand side, and the right-hand side is also contained in the left-hand side. So that is, we seek to show that this is contained in this, and this also contained in this. So let element X be in the first one, the left-hand side, and then we'll prove that it is in the right-hand side. Then after that, we'll prove that there's element X which is in this, which is also in this. Then we can say that they are equal. So let X be in A union B or union C. So this means that my X is in A union B. I open the brackets, A union B, and then I told you that we use or X is in C. We use or for union. So this means that my X is in A for this union, X is in A, or X is in B, or X is in C. Then I can rewrite this as X is in A, or X is in this, or can write it as union. So X is in B union C. Then when I move down, I can say that X is in A union. Then I can decide to put this one in a bracket. Not that I can decide that I put this one in the bracket. So X is in A union, then I open the bracket, X is in B union C. So since I've been able to move from here to here, it means that A union B in a bracket union C is contained in A union into bracket B union C. Okay. So that is the first one. Then the next one, I want to show that A union in a bracket B union C is also contained in A union bracket, A union B bracket closed union C. So I let X be in A union into bracket B union C. Then this implies that X is in A or X is in B union C, which is the same as X is in A or X is in B or X is in C. Then I can write it as X is in A union B or X is in C. Then this is the same as X is in A union B, I open a bracket, union C. So since I've been able to move from here to here, it means that A union B into brackets B union C is contained in A union B in a bracket union C. And since this is contained in that, and the first one is also contained in the other one, then it implies that A union into bracket B union C is equal to A union B in a bracket union C. Please, can I continue?
Yes,
Yes,
madam.
please.
Yes, please.
Yes, please.
Okay. So the next, I want to look at the distributive property. So I still have the set ABC. Then the distributive, I want to show that the distributive property says that A union B, so A is distributive over intersection. So A union B, then open bracket B intersection C is the same as A union B intersection A union C. And then is distributive over union. This is A intersection B in a bracket B union. You open a bracket B union C, close the bracket. Is equal to in a bracket A intersection B union A intersection C. So we use the same procedure we used for the first one to prove. So we can take the top one. So A union in a bracket, you open a bracket, B intersection C. We want to show that this is equal to this. And I told you, if this is equal to this, then it means that the left-hand side is contained in the right-hand side, and the right-hand side is also contained in the left-hand side. So that's what I want to show, that the left-hand side is contained in the right-hand side, and the right-hand side is also contained in the left-hand side. So if I'm able to prove that the left-hand side is contained in the right-hand side, and the right-hand side is also contained in the left-hand side, then it means that they are equal. So I'll pick an element X. So let X be in A union, then open a bracket, B intersection C. This means that X is in A or X is in B intersection C. So this will mean that X is in A, the or X is in. So remember I told you that or is for union and then end is for intersection. So when I come here, X is in A, or, so the or is here. X, so the union, X is in B, and S is in C. So X is in A or X is in B, and X is in C. It's the same as X is in A or X is in B, and X is in A or X is in C. So when I rewrite this one, this is X is in A or X is in B is the same as X is in A union B, and X is in A union C. And I know that the end is intersection. So X is in A union B in a bracket intersection. X is in intersection A union B. So I've been able to move from the left-hand side to the right-hand side. So this means that the left-hand side is contained in the right-hand side. Okay, so the left-hand side is contained in the right-hand side. Now I want to show that the right-hand side is also contained in the left-hand side. So I have X is in A union B intersection X union A union B. So when I open this, I have X is in A or X is in B, and X is in A or X is in C. This is the same as X is in A or X is in B, and X is in C, which is the same as X is in A or X is in B intersection C. And this implies that X is in A union B intersection C. So I've been able to prove that the left-hand side is also contained in the right-hand side. So I conclude that the left-hand side is equal to the right-hand side. So you can look at the second one. Then we have what we call De Morgan's law. So De Morgan says that A complement intersection B complement is the same as A union B or complement. And A complement union B complement is the same as A intersection B or in a bracket or complement. Then A difference B intersection C is equal to A difference B union A difference C. And then A difference into brackets. So the first one is intersection. And then the second one is A difference B union C is the same as A difference B intersection A difference C. So please pay attention. When it is intersection here, it is union. And when it is union here, it is intersection. So that one too, you go through the same process. You show that the right-hand side is contained in the left-hand side, and the left-hand side is also contained in the right-hand side. Okay. So A complement intersection B complement is contained in A union B or complement, and A union B in a bracket complement is contained in A, this is union, A complement intersection B complement. Okay. So I let X be in A union B complement. Okay, so I'm starting from here. Or here. So if X is in A union B complement, then we know that S cannot be in A union B. Do you agree?
Yes, madam.
Yeah.
So if X is in A union B, the complement, then it means that it cannot be in X union B. Okay, so X is not in A union B. So this means that X is not in A or X is not in B. So if it's not in the union, okay. Winnie, your hand is up.
Yes, madam. Madam, I wanted to ask, I decided to also start from A complement intersection B complement.
It's the same. You can decide from that place. It's fine. You get the same results.
Okay, madam.
So this means that X is not in A or X is not in B. So if X is not in A, then it means that it will be in the complement. So X is in the A complement, and the all here changes to end. So X is in B complement. So this means that my X is in A complement intersection B complement. So we've been able to show that first one, that A union B complement is contained in A complement intersection B complement. Then the next one, we want to show that the right-hand side is also contained in the left-hand side. So let X be in A complement intersection B complement. Okay. So if X is in A complement intersection B complement, it's the same as X is in A complement and X is in B complement. So if X is in A complement and X is in B complement, then it means that X is not in A or X is not in B. And we know that X is not in A or X is not in B is the same as X is not in A union B. If it's not in this, then it implies that it is in A union B or complement. And with that, we've been able to prove that A complement intersection B complement is contained in A union B or complement. So since we've been able to do the two, then we conclude that, okay, so the conclusion did not come. So we conclude that A complement intersection B complement is equal to B complement, B A union B or complement. Please, the concluding part didn't come. So I'll look at that one, but keep that one in mind. When you are solving it, you are supposed to bring that. So you can go through the same process to prove the other ones too. Any question? Any question? I want to continue.
Yes, madam.
Hello,
You
are
can
you
continue.
okay?
Yes, madam.
Okay, thank you.
Yes, madam.
So we want to look at two-set problem, and we've done that before. So we just want to look at this. So in the figure below, I hope you can even tell me what I is IV, R. So I have two sets A, B, which are subsets of the union set. What portion is I? How do we call I? I told you that what we're going to do here is the same as what you know. So what is I? Okay. Team, hey, this name there. See you, please. You know yourself. So please.
I is A
What is
intersection
I?
B. A intersection B.
I A intersection B. So let's write it down. We want to write it down. So you are saying that I is A intersection B. Then after that, we will look at what I also have. So he is saying that I is. Okay, so to him, I is A intersection B. Any other alternative solution? Do you all agree that I is A intersection B?
Yes, madam.
Yes, madam.
Okay. Now what about I? Let me open it. I. I and I. What is I? And I. Any hand up? Isa, what is I? Hey, Isa. Or Gifty, what is I?
A minus B.
Hello, madam.
Yes. Gifty, do we
I
have A
is
minus
A
B?
minus
We
B.
don't have A minus B. Please. Please let's listen to Gifty, then you come.
A minus
Gifty,
B
we
or
don't have
A
A
only.
minus B.
Okay.
A
I
minus
is
B
A
or
We
A
don't have A
only.
minus B. So let me take Gifty. We've not mentioned A minus B here. We don't have
A
A
A
only.
minus B.
difference B.
A only.
A only. Somebody is saying A. Somebody is also saying A difference B. Okay, so we have two. Is that all or any other alternative solution?
Madam, it is A intersection B complement.
Okay, so A intersection B. All B complement or all complements.
B
This is
complement.
it. This what I've written.
Yes.
Okay, is that all? Okay, then let's look at I. What is I?
Hello, doc.
Hello.
This is sir.
Okay, sir.
Doc,
What is
doc
I?
is A complement intersection B
A
or B
complements
only
or
or B
B
only.
only. Okay. Any other alternative solution?
B difference A.
B difference A. Okay. Is that all? Then what about Ivy? What about IVA? Am I online? What is about Ivy?
Madam. Madam.
Yeah, hello, I'm listening.
That is IV is A union B complement, all complement.
A union B all complement. Do you all agree? Or any other alternative solution?
Yeah, madam. It can also be A complement intersection B complement.
Intersection B complement. Is that all? Did you say A complement intersection B complement or hey, what did you say? Let me write it well.
Yes, it's A complement intersection B complement.
Intersection B complement. Okay.
Yeah, like this. Yes.
Like this. Okay. Is that all?
A intersection B all complement.
A intersection B all complements. A intersection B all complements. Okay. That's good. Let's see what I have here. I wish we can analyze it, but let's see. Let A and B be subsets of the universal sets mu, U. Every element X is in U. Element in U is a member of exactly one of the four distinct subsets of U represented by I, and I. Each of the regions are described in terms of A and B as follows. The region A is the elements belongs to A and B. It is therefore denoted as A intersection B. So we can see that this is A intersection B. So we are talking about element that belongs to A and then B. And then you said that it is, let me see. You said that, okay, it is A intersection B. So this is correct. Then let's look at the second one. We are saying that the second one, the element belongs to A only. So the one who said A only is correct. That is, they belong to A and not B. So they belong to A and not B. So it is therefore denoted by A intersection B complement. And I know that somebody said that. So it is denoted by, this is correct, this is correct. But let's look at A difference B. Okay. Somebody said it is A difference B. So A difference B, the definition, so the difference, what the definition we looked at here, we are looking at only two sets without the universal sets. Where is it? So we are looking at only two sets without the universal sets A and B. So it says that let A and B be the difference of the two sets is this. So this one you're talking about elements. So the difference here, if we talk about A and B, then we are looking at only A and B. So the difference, we want to look at elements that are in A, but not in B. But when we take this, we take the universal sets. And if we say that difference, then we are looking at A, and the focus is on the universal set. So if I pick A, then the difference will be the whole of everything except the shaded portion. Do you agree? Hello? Am I online?
Yes,
Can
madam.
someone hear me? When we talk about difference, then it means that we take only this one out, then the whole of this. So it cannot be only B. So this, we put this one somewhere because we are looking at the universal set. Okay. So the same thing, when we take the II2, this is correct. This is correct. Then we will take this one out. Thank you. Then the IV, it says the elements belong to none of A and B.
Please, Foster, your mic is on, Foster.
That is, they belong either neither A or B. It is therefore denoted by A complement intersection B complement or A union B complement. So that is it. It is in, it's not in A, it's not in B. So it is in A union B complement. And then from the De Morgan's law, we saw that A union B complement, or A union B or complement. A union B or complement is the same as A complement intersection B complement. Good morning. So the first two are correct. And then the last one says that it is A intersection B or complement. No, we cannot have A union B complement the same as A intersection B or complement. So this part, A intersection B, okay, so A intersection B or complements means that I'm taking A intersection B out, and we know that this is A intersection B. The A intersection B is I. So A intersection B or complement will contain I, and then IV. Please, do you agree that A intersection B in a bracket complement? It means that I'm taking A intersection B, which is I, out, then the whole of everything will be my A intersection B or complement. But here we are looking at only IV. Okay. So since it is IV, then it means that this one is not the answer, but the answer is A union B or complement, or A complement intersection B complement. Okay, thank you. We'll look at another one. So that is it. Okay. And it says that
Hello,
the
Doc.
region in the figure. Hello.
Hello, Doc.
Hello, I'm here.
Yeah, heading towards the region 2.
Heading towards the region 2.
Yeah, if I can't get you very clear, you cleaned A minus B. And
Yeah, I
region
cleaned
3
A minus B.
And region 3 to you clean B minus A.
Yes, please.
But madam, if, for example, let's assume that region 2, we are able to put X there.
Okay.
Then region 1, we're able to put 2, and region 3, we are able to put 4. Then we want to find for region 2, which is of X.
Mhm.
Automatically, it will be region 2 plus region 1, right? I don't know whether
I'm
madam
even
is getting
confused.
me clear. I am saying that
I'm even confused. Okay, so let me just give you a simple explanation of A difference B. I'm saying that when I talk about A difference B, then I'm talking about the set A and the set B only these two sets. So A difference B, it means that I'm taking the whole of this out. The whole of this out. But here we have A, B, and then outside. So I cannot say A minus B, A difference B, because the outside will not be part. Unless maybe I take the universal set and maybe A difference B, the universal set. Then I will talk about that one. So that one I'll talk about the elements which are in A but not in the other parts of the region. Do you agree? But the example, if
madam,
it is A difference B. Mhm.
Madam, in that case, the
I'm
region
listening.
4 becomes a disjoint to A and B. So at that point, we're not going to add the region 4 to that part. So we're only going to handle A and B, and that is where the A minus B comes.
At what point does the do we have disjoint something? I think I've seen a hand up. Amp, your hand is up. Festus.
Yeah, please, madam. I want to
Maybe
come in
you
a little.
want to help.
The description you are
Help,
giving.
help. Okay.
Madam, so if we are to use the difference, then one thing we need to take note is that with this one, we are solving the question in consideration with the universal set. So you can't get rid of the universal set. So in every
Yes, please.
means, in every time, you need to take into consideration the universal set. So if we are to use the difference, we can't say A difference B, because in that case, the universal set will not be considered. And the universal set is part
Outside,
of
that
the
is
question.
IV.
So
Part of the
I am
question,
thinking that if we are to use the difference, then to find for A only, then it means we will take it as A, we will take it as a universal set difference
A
B.
difference. A difference.
We are
A
finding
difference, the
A only.
universal.
No,
Yeah,
please.
so
The
it's
universal set difference B difference A union B or complement. Then I think that is where we get the A only.
Yeah.
okay. So this means that it cannot be A difference B only, because this
Yes,
one, the
please.
universal set of parts.
Yes, please.
Okay.
I don't know if our brother has gotten what we are saying.
So, madam,
Yes, yeah.
so if what you are saying, so for example, madam, you write this one, A minus A intersection B. Whether we can write it as the same thing.
A difference, please, is not minus. A
Yes,
difference.
A difference, A intersection B.
Intersection B.
Yes, all that, so that it will mean the same thing as region 2.
Is it the same as region 2?
No, please. Oh, it can
No,
be.
no.
No, it can't be the same. A difference, B intersection 2 is this one. So I'm taking A difference. So I'm taking only this one out. But what happens to the other side? So please, the focus is not on only A and B or A only. It's on the whole universal set. So please, you cannot take only A and B and then leave the universal set. So for this question, please, hello, there's a hand up. Ibrahim.
Madam, good morning. Madam,
Good morning.
Please, can you write the description of the sets or the regions, the description of the regions in the same page as where the figure is for us, so that it will be clear for us to see?
How? Yeah. In the
Yes,
notes.
please.
In
Yes,
the
please.
notes. But I see it's
Yes.
following.
Like,
It's
because they
here.
are not in the same page, no, it's not clear. The same page as where the figure is, the diagram. The previous page.
Okay. So this is a PDF file, and I don't know if I'll be able to rewrite it. Okay, so I will see if I can do that later.
Okay, madam. Thank you.
So please, you're welcome. Okay. So it says that the region in the figure above are connected by two sets of equation. So the number of elements in A union B, so the number of elements in A union B, so it's the same, the whole region is the same as the number of elements in A the number of elements in B plus the number of elements in the intersection. Okay, so we have or minus the intersection, the number of elements in A plus the number of elements in B minus the number of elements in the intersection. So I think we did this last time. So number of elements in A plus the number of elements in B minus the number of elements in the intersection. So last week we saw that if two sets are not disjoint, then the number of elements in A plus the number of elements in B minus the number of elements in their intersection is equal to the number of elements in the union of A and B. And then the third one, it says that the number of elements, the second one, the number of elements in the universal set is equal to the number of elements in A union B plus the number of elements in the intersection A union B all prime. So it's true. The number of elements in this universal set is, we have the number of elements in A union the number of elements in B plus the number of elements in the complement. The complement is the IV, the outside. So that will give me the universal sets. So now we are moving on to third and three sets problem. So in the figure below, ABC are subsets of the universal set. Every element X in U is a member of exactly one of the 8 distinct sets of U, represented from I to III to VIII. Okay. So same here. Let's see if we can answer all of them. We have I, V, and VIII. So let's see if we can solve this. So I'm writing. Please take your time and then answer the question correctly. So we have I, IV. So let's do the first form, then we'll continue. So what is I? What is I? Okay, Sheriff.
Madam,
Yes.
the I, it will be A intersection B intersection C.
A intersection B intersection C. Do you all agree?
Yes, madam.
Madam.
Or any alternatives to answer? Okay, what about I? Because of our time, I think we have to be fast. I is
Madam,
Madam.
the II is A intersection B.
A intersection B. Is that all?
Hello, Doc.
Hello, madam.
Hello, Doc. It's A
Yeah,
intersection
hello.
B intersection C complement.
Intersection B
A
intersection
and
C.
B only.
A and C only. A and C only. Okay. Any other?
B.
A and B only. Okay. Any other? Okay, let's
intersection
B only.
A intersection B only.
Madam,
Hello. Please, I'm here.
no, I'm good.
Okay, so let's look at III. III.
That's A intersection C only.
A intersection C only. Any other?
A intersection C.
A intersection C. Any other?
Madam, is A intersection B complement intersection C.
B complements intersection C. Okay, thank you. What about Ivy?
B intersection
B
C.
intersection C.
B intersection A. Okay.
B
Or
intersection C.
B intersection C.
or A complements A complements intersection B intersection C.
Is that all? The first one, is it B intersection A?
The first one is B intersection C, right?
Okay, so I should clean it. Okay, let's see. So this one, you are saying it is A intersection B intersection C. That one there, I will take that one. But the second one, you are saying A intersection B. A intersection B. Let's look at A intersection B. A intersection B is the circle A and then the circle B. So is A intersection B?
No, madam.
So we cannot take A intersection B. Okay, let me jump to this side. A and B only, or A intersection B only. So they are saying it is A intersection B only. Can it be A intersection B only?
Still no.
No.
Yes. Yes.
Okay, so the one who said yes, can you please tell me why it is yes? And the one who
We are,
said no, so tell me why it is no.
we are saying A intersection B only because that element can be found in only A and B, but cannot be found in C. That's why we said it is A intersection C only. Because if you add the region 1, meaning that the C is included, but when you exclude the C, the region 1, meaning that that element in that region 2 can be found in B and A, but cannot be found in C. That's why we are saying it's A intersection B only.
Only, okay. Then the one who said no, why do you say no? Hello, the one who said no. Or now you are saying yes.
Yeah, I would say yes because B only means that I is not part. So it's for only I. So I agree.
So now you are saying yes.
Yeah.
Let's continue. Then what about this? The I. A intersection C only. Do you all agree?
Madam,
Yes,
please. Please, madam, with the I. What about if you say A intersection B intersection C complement?
Oh, we didn't look at that one.
Yeah, you
Okay,
didn't.
so is it A? Okay. So it is okay, so you said it is A intersection
B intersection C complement.
Okay, so explain your answer.
Yeah,
Madam, like you just said, if we say A intersection B only, the intersection over there, I look at it as I and then I. giving you the A intersection B only. But then if you say A intersection B intersection C complement, it means the element there does not have anything to do or does not belong to C at all. That is why I will go for A intersection B intersection C complement.
Intersection C complement. Okay, that's good. Let's put it there. Then we'll look at the marking scheme.
Okay.
Mhm. So the last one. Are we done with the third one? Okay, the third one, you are saying A union, A intersection B complement. So that one is accepted. So how about A intersection C? Do you accept A intersection C?
No.
So that one is not in the options. But what about A intersection B complement intersection C?
Madam, that will also work.
That will also work. Okay,
Yes.
thank you. We'll compare it with the marking scheme. What about the last one, Ivy? You see Ivy. Ivy is here. So what is Ivy? You are saying it is B intersection C. Is it B intersection C?
No, madam.
So you will not take that
Madam,
one.
I'll go for A complement intersection B intersection C.
Okay, thank you. So let's see what we have here. Okay, it says that each of the regions are described in terms of A, B, and C as follows. So the region 1, the element belongs to A, B, and C. It is therefore denoted by A intersection B intersection C. So what you said is correct. So the first region, you said it is A intersection B intersection C. Then let's look at the second one. Second one, it says that the element belongs to A and B only. That is, they belong to A, B. They belongs to A, B, I think not in C. It is therefore denoted as A intersection B intersection C complement. So the one who said it is A intersection B intersection C complement is correct, or it is A and B only, or the same as A intersection. So we said that and is the same as intersection. So it's the same as A intersection B only, or A intersection B intersection C complements. So the third one will also be the same thing. It belongs to, okay, so that is the element belongs to A and B and not A and C and not B. So please here to not C, the not the come. And therefore denoted by A intersection B complement intersection C. So this one too is correct. And the last one. So the last one too. Sorry, so the last one too, as you said, is A complement intersection B intersection C. That's also correct. Then let's move on to the VI, and then and then VII. So what is V? A only, or
A intersection B complement intersection C complement.
let me write it. Okay, so you are saying so V is, please, you said V is A only, or A intersection B complement intersection C complement. Is that all? Am I online?
Madam.
Yes, madam.
Yeah. What about VI?
Madam, please, for the V, let me suggest one thing for clarification. Madam, please. The V. What about A intersection into bracket B union C prime? Like you close the brackets.
All complements.
Right. Yeah. Yeah. All
Look at that
complements.
one.
Okay.
Okay.
Madam.
Hello.
Madam, what about also writing it A minus into bracket B
Exactly.
union
We don't have
C
minus.
complement?
We don't have minus.
Oh, madam, A difference into bracket B union C complement.
Union C complement. Okay. A union C complement. Okay. Okay, that's your solution. What about the VI?
Madam.
Hello.
The VI. I think it should be A complement
A
intersection
complement
C intersection B. Yeah, intersection C complement.
Intersection C complement. Okay. Any other?
Madam, it's also B only.
B only.
B only.
Okay. Please give me about 5 minutes. Excuse me, I'll be with you soon. So just write your solutions. Then when I come, I'll just take it and then.
Please, am I the only person not hearing, madam?
No.
Okay. Thank you.
You aren't the one with the mic.
Hello.
Madam said she was doing something. She will get back to us.
All right.
Is any info? Madam Jessica, please, have you further from Madam why we are having this challenge?
Bro, it is not a challenge. She has made us aware that we should give her some time. She will return to us.
Sorry. I went off. Sorry. I'm sorry. I went off because of my network. That I didn't get that. All right. Thank you very much, sir.
Cool.
Hello. Hello.
Yes,
Hello,
madam.
madam.
Hello.
I'm
Hello,
so
madam.
sorry. I'm sorry.
Yo, you are welcome, madam.
I'm back. Okay, so let's continue. Okay, so you are getting it, so let's continue. The third one, the fourth one, we saw that. Then the fifth one, it says that the element belongs to A only, as you said. That is, they belongs to A and not B and C. It is therefore denoted as A intersection B complement intersection C complement. That's what you said. You said that it is A intersection B complement intersection C complement, or A only. Okay. And then the sixth one, the element belongs to B only. That is, they belong to B and not A and C. It is therefore denoted as A complement intersection B intersection C complement. And then the seventh one, the element belongs to C only. That is, they belong to C and not A and B. It is therefore A complement B intersection B complement intersection C complement. And then the last one, which is outside, it is, they belong not to A, B, nor C. It is therefore denoted as A complement intersection B complement intersection C complement. And we are saying the region in the three-set problem are connected by the equation. The number of elements in A union B union C, it is A union B intersection number of elements in A, number of elements in B plus number of elements in C minus the number of elements. Okay, so we open a bracket, number of elements in A intersection B plus number of elements in A intersection C and number of elements in B intersection C, then all minus the intersection of the three. So there should be a minus here. And it should be noted that the union set is the number of elements in A intersection, number of elements in A union B union C plus the number of elements in the A union B union C all complements. So that is A union B. So this is A union B, then plus the complement of A union B, A union C. That is it. So we have an example here. It says that a national football coach invited 18 players for a match. Out of these, 7 were attackers, 9 were defenders, and 12 were midfielders. The coach realized that 4 could play both in the attack and in the midfield, 6 in defense and midfield, and 2 play all 3 roles. Use set notation to represent the information. Illustrate the information in the Venn diagram. Find the number of players that can play exactly 2 rows and exactly 1 row. Okay. Okay, so we are using U to represent the universal, A for attackers, D for defenders, M for midfielders. And then we are told that the total number is 18. The attackers were 7, the defenders 9, and the midfield 12. And then we were told that 4 can play both attack and then midfield. And then 6 for defense and midfield. And then 2 can play all. Okay. So we are to write it in a Venn diagram. So we have attackers, defenders, and then midfielders. And then 2 can play all. 4 can play both attack and defense. Midfield, so 4, 2 plus 2 is 4. And then 6 can play midfield and defense. But we don't know the number that can play A and D. Okay. So I hope we can find C. X, sorry. Okay. So from this, you are told that this is, I'm running because I can see that I've done nothing. But if you don't understand something, you can just prompt me. You can also sit down to just look at it because these are just something that you have done before. So number of members in A union B unions, A union D union M is a number of members in A plus number of members in D plus number of members in M minus. So what we quoted, okay. So we're going to get 7 plus 9 plus 12 minus into brackets. We have 2 plus x, so we are adding this. We have 2 plus x, we have 2 plus 2, which is 4, 2 plus. So we have the whole of this set plus the whole of this set plus the whole of this set, then minus the intersection. So that's what we are doing. Okay, so this, then plus the whole thing is equal to 18. So when you add this, you're going to get 30. When you add this, you're going to get 12 plus x is equal to 18. And you simplify, this is 18 minus x is equal to 0. So it is equal to 18. So it means that my x is 0. So that people who can play both A, attack, and play So how do we get the exactly true? Hey, am I
Hi,
online?
madam.
Hi.
Madam, you are.
Please, how do we get the exactly true? Exactly true. Because in the question we are asked to find those who can play exactly two rows and exactly one row. So how do we get the exactly two?
Madam,
Mhm.
I think for the exactly 2, we are talking about the x, which is 0, plus the A intersection D complement intersection M, which is 2. And then A complement intersection D intersection M, which is 4. So we add the x, which is 0, and the 2 and the 4. We'll get the exactly 2.
Okay. Do you agree with him?
Yes,
Yes,
please.
please.
Okay. So exactly true is 6.
Hey,
Pacho, why? What about the exactly 1?
The phone aboho.
Hello,
Oh,
Doc.
sorry. Yes. Exactly 1.
The one is adding only the olis. The A only the olis. When we add all the olis, we'll get exactly 1.
So let's find A only. A only is
3.
7 minus 4, 3. D only is
5. 3.
and then M only is
4.
4.
so that would be
3
10.
plus 7 plus 3. Yeah.
it will be
10.
okay. So we
It will
have
be 10.
4, 3, 3, which is 10. Good. So you clap for yourselves. Okay, so there's another example here. So these are examples. You can take your time and then go through them. Okay, you have 2 examples. You can just look at them. This is a 2-set problem. In a survey of 100 students, 35 were registered in math, 52 in ICT, and 18 in both. How many did not register? So we can do that. So we have 18, and then we have 70. Okay, so do we have math only? We're registered in math, 52 in both. 35. Okay, so we have 35 minus 18 and then 52 minus 18. That will give us the only. And then we are asked to find those who did not register any course. Okay. So those who registered are 69. So when we subtract the 69 from this, it means that 31 did not register. So these are all examples. I think I cannot skip this. Let me just try and solve this. It says that write the set consisting of all possible outcomes when a coin is tossed twice. Use head and then tail. Okay. So we have a coin, then we toss it once, and then we toss it again. Okay, so we have a coin, we have head, and then head and tail. Head and tail. And then we have another head and tail. Okay, so when we are tossing it once, we're going to get head and head. We have head and tail. And then here we have tail and head. And then tail and tail. Let me see what we have here. It says that, oh, is that all? I was thinking where to. Okay, so the answer is head, head. Okay, so that's what we have. So we toss it one, we're going to get either head or tail. We toss this one, we are going to get head and tail. So when we combine them, we're going to either get head, 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 tail, tail, head, or tail, tail. Please, do you understand this?
Yes, please.
Yes, please. Madam, what if it is tossed 3 times?
And so you take this for the 4 one that we have here, then you have another head and tail, and then you pem them. Do you get it?
I do get it, but how to solve it systematically? That is what I was expecting.
So you can have your head, you can have your head, tail, you can have your tail, head, you can have your tail, tail. Then you can have your head and then your tail like this. So you're going to get head, 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 tail, head, tail, head, head, tail, tail. Then you can have your tail, head, head, tail, head, tail, 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 head, and then your tail, 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 like this. Are you okay?
Yes, please. But madam, is there any further question that they may ask concerning this one?
So for now, for this one, that is all. Unless maybe you want to find probability, but we've not treated that. Probability of obtaining exactly 1 head, or probability of obtaining 2 heads, probability of obtaining exactly 1 head or 2 heads or something like that. But for now, this is what we are doing now. Yeah.
Okay, thank you.
Okay, so these are all examples. You can look at them. Okay, so we are done with the initial thing about sets. The next one, we want to look at hello.
Hello, madam.
Madam.
Yes.
With regard to, I'm still coming back to the this in our only aspect, in a situation where a universal set is not given, I believe we can still treat the A
The
minus
difference.
B.
Yeah, the
Yes.
difference. Yeah.
Yes. Okay.
Yes, please.
Thank you very much.
You're welcome. Okay, so now I want to look at what we call the Cartesian products of sets.
Oh, madam.
Hello. Hello.
Please, can you go back to one of your previous slide? I just want to ask a question. I think
Hey,
yeah,
right. Yeah, we're not. We are not even done with this. We have other things to do.
Sure, madam, you do understand. But what I want to ask is when they say we are to prove that maybe A union this is equal to that one, you kindly take us through one step. I mean, one of the examples.
We have done it.
A union B is equal to B union A.
All right.
Is it this one?
Yeah, something like this. Yeah, sure.
Okay. So I told you that if you want to prove that A union B is equal to B union A, you have to prove that A union B is contained in B union A, and B union A is also contained in A union B. So thus, you show that A union B is contained in B union A, and B union A is also contained in A union B. So first, you take the either left or right hand side. So you take the left hand side, you choose X in A union B. And we know, I told you that we use or for union. So this means that X is in A or S is in B. And we can rewrite this as S is in B or S is in U. Then if I want to change the or to union, then I'll say that X is in B union A. So I've been able to move from the left to the right. So it means that A union B is contained in B union A. Are you okay? Then the next one, I have to prove that B union A is also contained in A union B. So I will let X be in B union A. Then this means that X is in A, X is in B, or S is in A. And this is the same as X is in A or S is in B. And if I write S is in A or S is in B, the same as S is in A union B. And I've been able to prove that A union B is contained, B union A is contained in A union B. So I conclude that X A union B is equal to B union A, because I've been able to move from the left to the right and right to the left. It means that they are the same. Is that what you wanted me to show? Hello?
Yeah, hello, madam.
Is it okay?
For me, I'm okay, but I just want to ask if maybe in the exams they ask, can we use numbers in place of what you've written, or we are just
please no, you can use numbers.
Okay.
Thank you. Let's continue.
Hello, madam.
Yes.
Yeah, please, may I ask you to do with the example one, the solution? So where we have the 7 plus 9 plus 12 minus, there is 2 plus x plus 4 plus 6 plus 2. In fact, I'm confused with the 2 plus the x. I know the x, but where we are adding the 2 with the x, that's where I'm not getting.
Is it this one?
Yes, please.
Okay, so from what we did, the 3 sets problem, we said that we are connected. So number of the elements in A union B union C is the number of elements in A plus number of elements in B plus number of elements in C minus number of elements in A intersection B plus number of elements in A intersection C plus number of elements in B intersection C plus, so this minus, there's a bracket here. So you subtract all the 2 intersection, then plus the number of elements in A intersection B intersection C. So with that, we were able to bring these things out. So using that equation, the number of elements in A, we had 7. The number of elements in D were 9, number of elements in M 12, and then the number of elements in A intersection D. A intersection D is this one, which is S plus 2. Then the number of elements in A intersection M, we're told the 4 of them can play both attack and midfield. And the number of elements in defense and midfield, we're told they were 6, so we have 6 here. Then plus, and we're told that 2 can play all, so that is 2, which is, and the total number of players invited were 18, so it's equal to 18. So when we add, this is 6 plus this is 10 plus this, which is 12. And this one, this gives us 30. Is it 30? 12 plus this is it up to 30? I think
30.
Okay, so adding the 2, so it's 30. So 30 minus 12 is 18. So 18 minus S is equal to 18, meaning that our S is 0. Is that where you were confused?
Yeah.
So are you okay now? Are you okay now, or you are still not okay?
I'm not okay with the 30. Is it 30?
Oh, okay. So let's add.
Madam, 60 plus 12 is not 30.
Yeah, it's not 30.
But please, it's not 30.
Let's add and see. This
Yeah,
plus
it's 28.
this.
It's 28.
This plus this. This plus this is what?
Yes.
That's
Plus
19.
2, so there's 30.
28 plus 2 is 30. There's 2 here.
Where from the 2? Where is the 2?
Those who
Because we
can,
only have minus.
those who can play all. So we have A, D, M minus the intersection of the 2 sets, or plus the intersection of the whole, or those who can play all. And in the question, we're told that and 2 play all 3 rows. So that is my 2. Are you okay?
Yes, please.
Hello. Festus.
Okay, madam, please. Then, if that is the case, we need to go back to when analyzing the 3 sets diagram.
Yeah.
At the last part, that is intersection of the A, B, and C. They don't bring anything here, so that should
I
have been
said
plus.
it's plus. Oh, yeah, it's plus.
Okay.
It's supposed to be plus. You are not multiplying. It's supposed to be plus.
Okay, thank you.
You're welcome. So are you okay now? Please, can I continue?
Yes,
Yes,
please.
please.
Good. Okay, let's continue. So we are looking at the Cartesian product of sets. Okay. We know that points in the Euclidean plane, you know Euclidean plane, right? Okay, so it's the same as the XY plane. When you are drawing anything, you write the XY plane. And we are told that the points in the XY plane are defined by the set R cos X. So we know that when you take the XY plane. So when I take the XY plane like this is X, this is Y. I know that I have 0 here. Then I have from negative 1 to negative infinity. And then on this, I have positive values to infinity. Yeah, I have negative to infinity. So I can represent the whole, this by R, and then this by R. You know R, right? Real numbers. Okay. So I can see the XY plane as S cross R cross R. That's what I'm talking about. The points on the Euclidean plane are x by x. So when I choose a point 2, 6, 2, 6, it means that I want the value 2 here and then the value 6 here. So I have 2, 6. This is 2, 6. This is 2, 6. But note that 2, 6 is not the same as 6, 2. Do you agree?
Yes.
Yes, madam.
Because if I write 6, 2, it means that I'm taking 6 from here and 2 from here. So 2, 6 is not the same as 6, 2, because here the order is important. When I write this, then I know that in the order, this 2 is for the x and this is for y. When I take this is for x and this is for y. So they are not the same, x and y. So for order is important. Okay, so let's continue. It says that we know that points in the Euclidean plane are defined by the set r cross r. So which is the same as r squared, which is equal to p such that p is equal to s comma y. And then my x is in r and my y2 is in r. Using similar notation, the Cartesian product of two sets x and t is defined as s cross t is equal to p such that p is equal to s comma t, small s comma small t, where small s is in big S and then small t is in big T. That is, s cross t is the set of all ordered pair. Please pay attention to the order. Ordered pair of elements s comma t, with the first member of each pair always from the set S and the second member always from the set T. So for example, if I have the set 2, 4 cross the set 2, 4, 7, this means that I'm choosing first element from the first set and then second element from the second set. So if I want to find A cross, so let me just pick. So if I have the set 2, 4, and then I have another set, so I'm crossing another set 2, 4, 7. I want to find the cross product. This is the cross product. It means that the first element should always come from the first set, and the second element will come from the second set. So I have it as 2, 2, and then these two will go to 4. So I have 2, 4. Then I have 2 to 7. So I have 2, 7. So I'm done with the 2 crossing with the elements here. Then I'll come here, 4 will go to 2. So I have 2, 4, 2. Then 4 will go to 4. I have 4, 4. Then the last one, 4 will go to 7. So I have 4, 7. This is how we perform the cross product operation. Are you okay?
Yes,
hello.
madam.
Yes,
Okay.
yes, madam. You're okay.
So we want to look at characteristics of the Cartesian products. So first characteristic is two elements of the set S cross B. So there should be a hand up. Okay, Foster. Hey,
Madam, please.
Mhm.
Madam.
Yes,
Doc, please, in a situation whereby the set containing 3 elements before the set that contains 2 elements, what do we do?
Hey, Foster.
Madam.
You should be able to do this. So it's the same thing. I can bring the 3. So 2, 4, 7 cross 2, 4. This will give me. So I'll pick 2 to 2. So 2, 2. Then 2 to 4. So 2, 4. Then I'll pick 4 to 2. So I have 4, 2. then 4 to 4. Then I have 4, 4. Then I'll pick 7 to 2. So I have 7, 4, 7, 2. Then I have 7, 4. Are you okay?
Yes, please, madam. Thank you.
So note that the first term is always coming from the first set.
Okay.
Okay, so the characteristics, the first one, it says that the elements of the set A cross B are equal if and only if they are identical. So if I have a S cross B, we are saying that the elements in S cross B are equal if only they are identical. So let me say that I have S comma T. If S comma T is equal to A comma B, then it means that my X is the same as my A, and then my T is the same as my B. So that's the first characteristic. Then the second one that says that if I have two sets, S and T, if my S is empty set, and T is also empty, then A cross S cross A. Well, I don't know if it's how many is back. Then S cross T will be equal to the empty set. Sorry. So if S and T are empty, then their cross product will be empty. Fuck that. Pastor, your hand is up. Pastor, your hand is up.
Is it and or? Hello.
Yes.
Madam, please. Is it and or?
Or this or. So if
it means if any of them is empty,
so if
you
A
will get
is
an empty set.
If S is empty and T is not empty, you still get an empty set.
Okay.
Thank you. And if both of them are empty, you get an empty set. Thank you very much. And then the third one says that clearly S cross T is not equal to T cross A, and we can even see it here. Here we have two sets. We had two sets. We had this. And then when we found the cross product, we had 2, 2, and this. But when we changed the position, we saw that what we are getting is not the same. We have 2, 2, we have 2, 2 here, 2, 4, we have 2, 4 here. We have 4, 2, we have 4, 2. We have 4, 4, we have 4, 4. We have 2, 7, but there's no 2, 7. We have 4, 7, there's no 4, 7. Okay. So we are saying that ST is not equal to TS unless S and T are the same. If S and T are the same, then you are going to get ST to be equal to TS. But if they are not the same, then ST is not equal to TS. So it says that if S comma T is in S cross T, we cannot have S comma T in T cross S. And we saw an example, the one we solved. Then the fourth one says that
Done.
Yes, Abudu.
That means if the question that we just solved, if in example you are being asked to prove whether it is commutative or not, you conclude by saying it is not commutative, right?
Hey, I've not written any commutativity here.
I know. Last block we did this. We those who are doing IT, we did mathematics for computing, and this same question came. Okay. So the same thing like this, and they asked that we should prove whether it is commutative or not.
Okay.
That's why I'm asking this on them.
So is it a cross product? Is it on cross products? Cartesian products?
Yes, madam.
It was on Cartesian products.
Yes, madam.
Okay, so we can see that they are not the same unless S and T are the same. If S and T are the same, then S cross T will be the same as C cross S. But if they are not the same, then S cross T cannot be equal to T cross A.
No, they were not the same.
Have I answered you? If they are not the same, then they cannot be the same. The product of S and T cannot be T cross A. The only time it can be the same is when one of them is empty, as your friend asked.
Okay.
Is it all? So if one of them is empty, let's assume T is empty. If T is empty, then S cross T will give me a null set, and T cross S will give me a null set. So the only time S cross T will be equal to T cross S is when one of them is empty, or they are the same. If S and T are the same, then the cross will be the same. But if not, then it cannot be the same. Are you okay? Hello, can I continue?
Yes, madam. Yes, madam.
Okay. So the fourth one, the Cartesian product of n sets. So if I have the sets S1, S2, S3, S4, S5 up to n, then the cross product will be S1 cross S2 cross S3 cross S up to Sn. And this is equal to X1, S2, S3 up to S, and such that my first S1 is in S1, X2 is in S2, and then Xn is in X1, and that is the fourth one. So that is if I have SIs, where SI is equal to S, where I is equal to 1, 2, 3 up to N. So then my S1 cross S2 cross S3 cross S4 up to cross Sn can be written as S to the power N. So just like I said that the Cartesian product S cross R can be written as, so R cross R can be written as R squared, because I just said that they are. So R cross R is the same as R to the power 2, because there's a real number, there's the real number. So if I have S1, the same number, and then S2, which is the same as X, then I can write it as S cross S, which is the same as S squared. And if there are 5, I can write it as S to the power 5. So example, it says that we should prove that A cross B is equal to B cross A, if and only if A is equal to B, or at least one is empty. So I even just said it. I said that the only time S cross B, the only time A cross T can be equal to T cross A is when one is empty or they are the same. So this is the example you have to prove that A cross B is equal to B cross A if and only if A is equal to B or one is empty. So first we'll start by saying that A is equal to B. That's the first part. If A is equal to B, then it means that my A cross B is the same as B squared, because they are the same, or A squared. So A cross B is equal to B to the power 2 or A to the power 2, which is the same as B cross A. So that's the first one. On the other hand, if A is empty or B is empty, from the characteristics, it means that A cross B is equal to a null set, or B cross A is a null set. Okay. Therefore, A cross B, if this is an asset and this also an asset, then it means that A cross B it means that A cross B is equal to B cross A, because we know that both of them are null sets, or one of them is a null set. So that is it. But when A is equal to B, or A is empty and B is empty, so that is if A is empty or B is empty, then the cross product of A cross B, Cartesian product of A cross B will be the same as BA. So let X cross B be equal to then that. So the next one, we want to look at when both of them are not empty. So let A cross B be equal to B cross A, and let A not be a null set and B not be a null set. Then it means that we have an element in A. So let the element in A be small a, and the element in B be small b. Since both of them are not empty. Then since both of them are not empty, it means that A cross B will give me A comma B. So I am going to obtain A comma B in A cross B. But I'm saying there A cross B is equal to B cross A. So if A cross B is having A comma B, then I should have A comma B in B cross A too. Like this, since A cross B is equal to this by assumption. And if it's like that, it means that, so if it is A comma B is equal to A cross B, then it means that my A, small a is in big A and my small b is in big B. When I come here, I have A comma B in B cross A. This part also means that my small a is my B and my small b is my A. Okay. So for this part, it means that small a is in B and small b is in A. If I'm able to, I've been able to prove that this same A is in A and this same A is in B. It implies that my B is contained in A and my A is contained in B, because I have my small a which is in A and my small a which is in B. I have my small b which is in B, my small b which is also in A. So since it is like that, it means that my B is contained in A and my A is also contained in B. And then we learned today that if A is contained in B and B is also contained in A, then it means that they are equal. So this means that my A is equal to B. So A cross B will be equal to B cross A if both of them or one of them is empty. If both of them or one of them is empty, then they are going to be A cross B will be equal to B cross A. Or if they are the same, the two sets are the same. If A is equal to B, then my A cross B will be equal to B cross A. And that's what I've done here. Then example 2, we have the set ABC defined by this, and we want to find the Cartesian product of A. So first I want to find Cartesian product of A cross B cross C. So my A is x1, x2, my B is y1, y2, and my Z is z1, z2. So I want to find the cross, as we said. So it means I'll pick the first one from A, the second one from B, and then third one from C. So I have x1, y1, x, z1. Please, are you okay?
Yes, please.
Yes, madam.
Then I'll pick x1, I'll pick y1, and I'll pick z2. Then I'll pick x1, I'll pick y2, and then I'll pick z1. Then I'll pick x1, I'll pick y2, and then I'll pick z2. So I'm done with the x1. Then I'll come to s2, I'll pick s2, y1, and then z1. So that's what I have. Then I'll have x2, y1, and then z1. Then x2, y2, z1. And then x2, y2, and then z2. So that's how I do the cross Cartesian products. So let me just try, and then let's try and write one out. Hello, there's a hand up. Please, you can talk.
Madam, with the one you just crossed now, I just want to ask, the way we did the probability, the head and tail tossing of a coin, I don't know if we do the same thing for x1, y1, and then now we come and do it for the x1, y1 combined with the z1. Can we be able to get the same outcome?
Okay, so I've not tried that one. So let's try it now and see if we're going to get the same thing. So I have x1, x2. I have y1, y2 like this. So let's cross it. I have Okay, I want the x because I want the x to be first. Okay. Because yes, so this x1, x2, y1, y2. So I'll pick x1, y1, x1, y2. Okay, then I'll have x2, y1, x2, y2. I've not tried this one before. Then I'll come and then I'll have z1, z2. And this I had x1, y1, x1, y2, x2, y1. I've not tried this before. So just x2, y2, and I think you may get the same thing. So I'm going to get x1.
The second one is
The second one is x1, y2.
x1, y2, okay. So I have x1, y1, z2. Then I have x1, y2, z1. Then I have x1, y2, z2. And I will have x2, y1, z1, x2, y1, z2. Then I have x2, y2, z2. Then s2.
Madam Z1.
Hey, that's z1. s2, y2, x2, z2. So let's put all of them in a bracket. So we're going to get x1, y1, z1, 1, 2, 3, 4, 5, 6, 7, 8. I think it's the same because when I'm supposed to get 2 times 2 times 2, which is 8. And I think when you write it in this set form, you are going to get the same thing. So I think when you do that, you're going to get the same thing.
Okay, thank you, madam.
You're welcome. So we can even try it with this. It says that construct all possible points x cross y such that x is in x and y is in y. Then we have this. So let's try this one with what you just, that table form. But what we need is the outcome, not the table. So you can do the table somewhere and then, so we want to find x1. So we have a cross b. Then we'll have our table x1, y1. And this is y1, y2, y3. So this x1, y1, x1, y2, x1, y3. Y1, hey, this x2, so it's x2, y1, x2, y2, and then x2, y3. It's supposed to be 2 times 3, so 1, 2, 3, 4, 5, 6. So the set will be x1, y1. That's what I'm looking for. A cross b is equal to, okay. Then I have x1, y2, then x1, y3, then x2, y1, x2, y2, and then x2, y3. Okay. So that's what I'm looking for. x1, y1, x1, y2, x1, y3, s2, y1, s2, y2, s2, y3. So that's what we want. So that's what I want. So you can do the table somewhere and then write it, one answer for me. Hello. Foster.
Hello, madam. Madam, please, can you go to the slide? No, the construct. Yes, please. So, okay, thank you. So, constructing all possible how do you call it, point X and Y, where we are having A cross B. The X1, Y1, was it provided by the question or we computed that?
Oh, it's supposed to be. So this was provided by the question.
Okay,
So it
thank you
says
so
that
much.
your A is this and B is this. You're welcome. So construct all possible triplets X, Y, Z such that X is in A, Y is in B, and Z is in C. Okay. So this one, X, Y, Z, you can use the table and you'll be able to get all the outcomes. Okay. One, two, three, four, five, six, 7, 8. 1 is 3. Okay.
Madam,
So
so
2
at that
times 2,
instant,
12. Mm-hmm.
but at that instant, which one are we using to multiply the X, Y, Z?
This is X. This is for A. This is for B. This is for Z. So you pick X, you pick Y, you pick Z. Always make sure the S comes first.
Madam,
Because this
please.
is the first one.
Madam.
Hello.
Yeah. Looking at it, we have A multiplying B multiplying C. But when you get to the Z aspect,
It's
we
not
have
it's not
Z1.
multiplying, you know.
Okay.
It's not multiplying. We call it cross Cartesian
okay.
Cross product, or maybe Cartesian product, please.
Okay, thank you, madam. But why is it that the Z aspect is as Z1, Z2, Z3? But
Okay, so we're
X
supposed to was supposed, so it means that it's supposed to be in the question. That X is A is X1, S2, B is Y1, Y2, and then C is X1, Z1, Z2, Z3. So it's supposed to be in the question somewhere. Maybe the question. Okay, see where A is
right.
X1, B is this, and then Z is this. So it's in the question.
Okay.
Thank you.
So to cross-check your answer, you know this is 2. This is also 2. This is 3. So it's 2 times 2, which is 4 times 3. So this is 12. So you should keep in mind that you are supposed to get 12. And you shouldn't get repeated sets. It's supposed to be the same. Difference. Sorry. So this will give you 12. This will give you 6. This will give you 8. So they were given in the question, please. The A and B were given in the question.
All right, let's proceed.
Yes. Please excuse me. Let me put this phone. Yeah.
Doctor,
I'm good. Hello. Hello.
Yeah.
Yeah. Into my phone fellow from the Charlie.
And I'm sorry. Sorry. Don't worry.
Window now and wabble phone.
Oh, sorry.
But I'm marking to buy one for you. Don't worry.
I am here doing
Hey,
BNC.
John, Mr. John.
Oh, okay. So we are still here. So that is it. And another okay. So in the above example, see that for the A, number of A is 2, number of B is 2, and number of C is 3. So for the resulting product, the number of A cross B cross C is supposed to be 8. So we just said it. And then for the other one, we had my screen not showing. Are you sure? Please, is my screen showing?
It's now showing.
Is it now?
Yes, madam.
It's gone.
Okay. So as I said, you will just look at the number. You know that it's showing. So check your network. So for all of them, the third one, you saw that it's going to be 2 times 2 times 3. Please check your network.
It has come.
Hey, check your network, please. So the result in this example shows that the elements of the Cartesian product of any number of sets is the product of the number of elements in respective sets. In the next example, we consider a condition under which Cartesian product is associated. So we want to prove that A cross B in a bracket cross C is equal to A cross in a bracket B cross B. If and only if at least one of the sets A, B, C is empty. So we did that. So in the characteristic, we are told that if or all of them are empty, then we're going to get an empty set. If not, then the associativity will not hold. So let A cross B be empty, A, B, and C be empty. Then we know that A cross B in a bracket cross C will be empty, and then also A cross in a bracket B cross C will be empty. Because if one or all of them are empty, then you're going to get an empty set. Then the next, I suppose that A cross B in a bracket cross C is equal to A cross B, open a bracket, B cross C. And then my A is not empty, my B is not empty, and my C is not empty. If A and B and C are not empty, then we know that A cross B cross C will treat the A cross B as one set. So we have an element X in A cross B. And then we have element Y in C. So it's not empty. So I'll have X in this. So this will mean that my X is in A cross B and then Y is in C. We put it down there. So that is for this one. Then the second one, I'll have S cross B. This sets, this one, it means that X is in A and then Y is in A, B cross C. So that is X is in A and B is in Y cross C. Now X is in A and X is in A cross B is a contradiction because we're told that X is in A cross B. Now we are saying that X is in A. And this is a contradiction because we are expecting X to be in A cross B. But here we are saying it is in A only. So this is a contradiction. So since it's a contradiction, then we can say that A cross B in a bracket cross C is equal to A cross into bracket B cross C. So the assumption that A is not empty, B is not empty is false. Therefore, for the associativity to hold, then my A cross B cross my A, B, and C are supposed to be empty. If they are all empty, then the associativity will hold. If not, if they are not empty, then it cannot hold because my X cannot be in A and then B in A cross B at the same time. So that is the proof for that one. I want to continue with our example. It says that let A be X such that, okay, X is less than or equal to 2, X is greater than or equal to 1. And then I have my B, X is less than or equal to 3, X is greater than or equal to -1. We are asked to sketch and describe the graph of A cross B in the XY plane. So when I pick my A, so we are told that A is equal to the set one less than or equal to X less than or equal to 2. This is my set A. And my set B is negative, so B is -2, this. And I want to find A cross B. When I open this set up, my A will be 1. 1, between 1, I can have 1, 0.00, 1.00000000000001, so many points. So I can write 1, and then I'll bring some dots. Then I'll write 2. Sorry. I can even write 1.5. So I have 1, some dots before I get to 1.5. Then after 1.5, I have a lot of numbers here. Infinite. Set B. I have -2. Please excuse me. Let me. So many steps. Okay, so as I was saying, when you pick A, you have 1, and before you even get to 1.1, you have infinitely many points. Before you even move to 1 point, ample for your hand is up.
Okay, yes, please. Madam, is it because they did not specify the kind of set they want in the set builder notation? That is why we can have 1.000001 and so on and so forth.
Okay, so it's because we want to sketch. We want to sketch. So here we are told that X is greater than or equal to 1. So greater than or equal to 1, you know that from between 2 and 1, you know that you have infinitely many points. Do you agree? It's greater.
Yes,
We are
madam.
saying it's greater than 1. Greater than or equal to 1. So any number before 1 is greater than 1. Between 1 and 2, maybe 1.1, 1.05, 1. So we are talking about numbers greater than 1. And then 1 itself. then we are looking at numbers less than 1. And so we are not looking at only the is it integers, so 1 and 2, but this we are talking about numbers greater than 1 but less than or equal to 2. Are you okay?
Yes, please.
Okay. So when we pick the other set 2, we have -2 because it's parts. Then we have so many points before we get to -1. Then we have so many points before we get to 0. Then we have so many points before we get to 1, so many points before we get to 2, and so many points before we get to 3. Okay. So the cross product A cross B, we said that the first set is always coming from A, the first one. So I have 1 and a -2. Then I can have 1. So I have some points. I can have 1 and then I have -1. So I have 1 -1. Then there are some points before I have 1 and then 0. Then I have other points before I have 1 and then +1. Then I have some points, I have 1 and then 2. Then I also have 1. So some points here, so I have 1 and 3. That is for 1. Then I can pick 1.5 and then -2. Then some points before 1.5 and then -1. Some points 1.5 and 0. Some points 1.5 and then 1. Some points 1.5, 1.5 and 2. Then I'll have 1.5 and 3. So some points here, all starting with 1.5. Then I can also have I can choose the last one, which is 2. So I have 2 and then -2. Still on the set, so we are not done. Then I have 2, so some points here, 2 and -1. Some point 2 and 0. Some points 2 and 1. Some point 2 and 2. What? Is it okay? Martina, are you okay? Please excuse me. Hello. Then I have some points and then 2 and 3. So I want to try and sketch that. So I have my XY plane. So first one, I have 1. Maybe I have 2 here. And this one I have, it's supposed to be -1 and +3. So the first one I will choose, is it 1? Okay, so this one, sorry. This is supposed to be 1. 1 and 2. So the first one I will choose, this -2. Is it -2? Are you with me?
Yes, ma'am.
-2.
Okay, so I'll plot the points. +1. +1 is for X and then -2. So I'll plot it here. Then I'll plot the points +1 and -1. So +1, -1. I'll plot the points 0, positive 1 and 0. It is here. Positive 1 and 1 is a point here. Positive 1 and 2 is somewhere here. Positive 1 and 3, it's here. So I'm done with that one. Then I'll go to 1.5. So maybe 1.5 is here. I'll choose 1.1, 1.5 and 2, 1.5 and negative 1, 1.5 and 0, 1.5 and 1, 2 and 3. It's here. Then I'll choose positive 2 and negative 2, positive 2 and negative 1, positive 2 and 0, positive 2 and 1, positive 2 and 2, positive 2 and 3. So these are the points I was able to write out. But the dots, it means that I can choose another number, maybe 1.10, 1.10 and then 2. So I can choose points between here and here. These are all points. Then I can choose some points on this line. I can choose some points here and then here. All these areas are points. So I'll shade all of them, meaning that they are part of what I'm looking for. So I'll shade. So the graph, what I want to sketch is this. But everything is shaded because they are all parts of what I'm looking for. I cannot write the points down, but I'll shade them. That's why I use the dots, 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 dots. So you shade. So that's what I'm looking for. So the question says that I should sketch and describe the graph of x cross b in the xy plane. I'm done with the sketching. Can you describe it for me? What is it? Can you describe this?
I think it's a rectangle.
It's a rectangle. And then you can talk about the vertices. So the vertices we have -2, +2 here. Here we have -2, 1. Here we have 1, 3. And then here we have 2, 3.
Hello, madam. Please, I think the point has been interchanged.
Yes, it should be +1, -2.
+1, where is it? Oh, sorry. Yes, it's true. It has been interchanged. Thank you. It has been interchanged. It's supposed to be +1, -2. This is +1, +3. Thank you. And this one is +2, -2. Thank you. Okay, so you sketch it, and it is shown that in this one is not showing. It says that the graph is a set of all points. It's a set of all points in the rectangular region in the plane with vertices 1, -2, 1, 3, 2, -2, 2, 3. There is a hand up. Jacob. Jacob, your hand is up. Oh, it was a mistake. Let's continue.
Yes, Doc.
I'm listening.
Doc, I said that the middle line that you introduced, is it relevant that we should bring it there before we shade it?
Oh no, it's not. It's not by force. You can decide not to bring it. But I just wanted to tell you that there's other points. So you can just bring the end point, and then you tell us that all these are part of it.
Okay, thank you so much.
Okay, thank you. You're welcome. So there's another example, X, and then I have A and B. So you go through the same procedure. You know that the X is supposed to be, X is less than or equal to 2. So this one, less than or equal to 2, you can start from infinity. You come to 2. And this one is between 1 and -1. -1 and 2. So you can just have your graph like this. Martin, is she okay? Matt, Adamawa.
Oh, no, I'm finished.
But what is it here?
I already did.
Okay, so thus we have A is equal to S less than or equal to 2. And then I have B is equal to the set -1 less than or equal to 3. So you can write that out that when I sketch, I have my X and Y. My Y is between -1 and then +3. My X is less than or equal to 2, so I have +2 here. So I know that the graph will take this form. Sorry, it will pass through 2, and then I'll have my 3. So let me just try and sketch it like this. Something like this. It should be one is this is part, this is part. But this one in the graph, we're told that it is less than 2. So it means that it is going this way up to infinity, like this. It will be something like this. So you shade the whole of this. But you can take your time and write the points. My point A will be the set starting from infinity to 2 like this. And then my set B will be from -1 up to 3 like this. Then you can just, so you have some points before, so A cross B, you have some points before you start with the sets. Do -1, you have some points, then you have 2, 1, or 2, 0. Okay, so you can look at 2, 0. You can have 2, 0. Then you have some points before you get to 2, 1. You have some points, you get to 2, 2. Then you have some points before we get to 2, 3. So it's like that. But when you sketch, you're going to get something like this. You can also have some 3D examples. Okay, so these are exercises you can go through. When do you go for break?
Please now.
Is it 10?
4 minutes.
Okay, so you have 4 minutes. Yeah, let's do some few minutes, then we go. Chairman Foster, your hand is up.
Yes, madam, please, the last example that you solved.
Okay.
Well, with regards to the first one, we're able to find the vertices of the quadrilateral, or as called the rectangle as well. So in the situation for the second, how do we also describe it in case we are asked to describe it?
The second one too, it also looks like a rectangle, but it ends at infinity.
Okay.
Then you can talk about something small about the endpoints. I think that's okay. So this one, but you can talk about this end. Something. This is 2, 3, and this is 2, -1. So you can talk about this point, and then the rest is going to infinity.
Okay, thank you.
You're welcome.
Madam, please can we label the infinity side as negative infinity, like if you want
Okay,
to
yeah, it's
write
moving
the
to
vectors
negative.
down.
It's moving to negative infinity, not positive infinity.
Okay.
Madam, please, I'm quite struggling with how you presented the A and B values on the graph. Let me put the graph. Can you guide me?
Is it the first one, or is it the first one or the second one?
Just the Yeah, the second, just the, yeah, this one.
Okay, so I have the point here. So A cross B, I know that there are points, other points before that, but I decided to choose 2, 2, -1, 2, 0, 2, 1, 2, 2, and 2, 3. So I have 2, -1 is here, 2, 0 is here, 2, 1. If this is 1, this is 2. So I have 2, 1, 2, 2, and then 2, 3. So I'll just draw the straight line. And then I know that the values are supposed to be less than 2. So I can choose 1. So I can have 1, -1, 1, 0, 1, 1, 1, 2, and then 1, 3. I can choose 0. 0 is less than 2. So I can have 0, -1, 0, 0, 0, 1, 0, 2, 0, 3. You can choose any number, maybe -5. So -5, -1, -5, 0, -5, 2. So you see that when you choose them, it will be in a straight line like this. The
Okay.
endpoint will always be 3 and 1. Then you shade.
All right. Thank you.
You're welcome. So after the break, we'll look at the real number system. So when we talk about the real numbers, we are talking about the set of all types of numbers, but it excludes the complex numbers. So we are talking about the real numbers. So we are talking about natural numbers. We know what natural numbers are. Natural numbers is the same as the counting numbers. And the notation is n, this n. So we are talking about 1, 2, 3, 4, 5, up to positive infinity. Then we have the whole numbers. The whole numbers is the natural numbers, but this one, 0 is included. Okay, so we have 0, 1, 2, 3. So we can write the whole numbers as okay, so I have whole numbers. Whole numbers, I can write it as whole numbers W can be written as the sets, can be written as, okay, so a set containing 0 union the natural numbers. So that is my whole numbers. Then I can also talk about the integers. When we talk about integers, we are talking about the negative numbers plus 0 plus the whole numbers. Then we can also talk about the rational numbers. When we talk about rational numbers, we are talking about A over B, where A and B are both real numbers, but my B cannot be 0. So the rational numbers is a number that can be represented as a fraction like this, or numbers whose decimal representation either terminates or recur or repeats. Okay. They either terminate, they recur, or they repeat. Then we have the irrational numbers. These are numbers whose decimal representation do not terminate or recur, but everything combined. So the whole numbers, integers, the natural numbers, they can all be written as rational numbers. So if I take 2, I can write 2 as 2 over 1. So I can write it as a rational number. When I take -3, I can write it as -3 over -1. Or I can write it as -6 over 2. So they all fall under rational numbers. So these numbers, they are subsets of rational numbers. So rational numbers were represented by a Q. I said we use N for natural numbers, the same as counting numbers, W for whole numbers, I or Z for integers. So when you are reading any math book, and then in the book you see that there's a number given X in Z, then you should know that X is an integer, or given X in I, so you're talking about the number that you are playing with is an integer, or maybe X in N, then you should keep in mind that the number you are playing with is a natural number. We'll get to a point, we'll not mention natural numbers, but I will just give in, so maybe we'll get to differentiation and giving a number x in n. So it means that the x we are talking about is a natural number. X in w, x in z, so it's an integer. You will get to abstract algebra or other mathematics, other topics, and you see we'll be using Q, knowing that you know that Q is rational number, and you know what a rational number is, or giving something in I. When we say giving something in I prime, it means that we are talking about irrational numbers. When we talk about R, then we are talking about both rational and irrational numbers. So rational,
Please, is it K prime being the irrational? Because you
irrational,
said I.
yeah. So sorry, so Q prime being irrational. So when we talk about R, when I pick R, so I have my R, and then under R, I can have my Q and then Q prime. And then under my Q, I can have, under my Q, I can have, what do you call, integer. So I have integer here. Okay. And then under the integer, I can also talk about whole numbers. Okay, whole numbers. So I can have whole numbers. Whole numbers. So the whole, under this one, I have the whole numbers, then I have the negative values. Okay. And then under the integer, I have this, then I have the fractions too. Fractions. So under Q, I have the integer, I have fractions. And then under the integer, I can have the negative values, negative whole numbers, and then negative values, and then the whole numbers. And then under the whole numbers, I can have my 0, and then I can have my natural numbers. So we can represent it like that. Or you can even write it in the set form. You can have your Venn diagram. You have your R, and then in the R, you're going to get your integer. Okay, so your R, you have your R here. In this, you have your Q. Then outside the Q, so this is my Q. This set is my Q. And then outside is the Q prime. Okay, then inside the Q, I can have my integer. So integer is inside. Then after the integer, I can have my whole numbers. So this is my I, this is my W. Then after W, I can have my N. So I can represent my real number system as this. So N is here. There's a hand up. Hassan, your hand is up.
Yeah, madam, please. So how can you represent the real numbers?
The real numbers. That's what I've done here in the Venn diagram. So I have Q, I have my R. I have Q and I have Q prime. I have I here. So this is my Q, this is my I, this is my W, and then inside is my N. That's it. That's my R. Welcome. Okay. Okay, so we go for break and then come back. We'll start with the property. And I trust coin. So that one I go. The break is for how many minutes? The break is how many minutes?
Madam, since you want us to close early, let's make the break 10 minutes.
The break 10 minutes. Okay, let's continue. So we want to look at properties of real numbers. So we can talk about equality properties. So under the equality properties, we will look at if I have ABC in R. So ABC in R, I mean ABC are real numbers. Then the first property we'll look at, we call it the reflexive property. When we talk about the reflexive property, we mean we have the left-hand side equal to the right-hand side. So if I have anything, my right-hand side equal to the left-hand side, then it means that that thing obeys the reflexive property. Okay, so if my A is equal to A and B is equal to B, that is the reflexive property. So I have A into bracket B plus C is equal to A into bracket B plus C. This is reflexive property. And in other words, we can say in relation, we have what we call relation. In relation, we can have A, R, A, and we read it as A relates A. So when you talk about the reflexive property, we cannot talk about the greater than or less than. The greater than and less than are not reflexive. We are talking about equal to. Then we have what we call symmetric property. Okay. Symmetric property says that if A is equal to B, then my B is equal to A. So example, if I have R and my R represent brother, then brother of, I can say A is Kofi and B is Kwesi. Then I can say that Kofi is a brother of Kwesi, and it should mean that Kwesi is also a brother of Kofi. So that is the symmetric property. So if Kofi is a brother of Kwesi, then Kwesi is a brother of Kofi. So Kofi is a brother of Kwesi and Kwesi is a brother of Kofi. So if A into bracket B plus C is equal to AB plus AC, then it means that AB plus AC is equal to A into bracket B plus C. And this is the symmetric property. Then we have what we call transitive property. The transitive property says that if A is equal to B and B is equal to C, then it means that my A is equal to C. So if A is equal to B and B is equal to C, then it means that my A is equal to C. So if A relates B and B relates C, then it means that A will also relate C. So if, let me take, if Mr. Odro relates Festus and Festus relates Mr. Edu, John Edu, Mr. Odro relates Festus. Festus relates Mr. Edu. Then it means that Mr. Edu will also relate, Odro will also relate Mr. Edu. You should be able to do it yourself. Please, are you okay?
Yes, madam.
Yes, madam.
Yes. Mr. Odro relates Mr. Chairman Foster, and Chairman Foster relates Mr. John Edu. It means that Mr. Odro also relates Mr. Edu, and that is the transitive property. So example, if A plus B, or in a bracket, times C is equal to A in a bracket A plus B, and A in a bracket C outside A plus B is equal to this, then they are the same. So that's the transitive property. So that is, we call all of them put together, we call them the equality property. Okay, we have another one here. So that is the substitution property. It is also under the equality property. It says that if A is equal to B, then A can be replaced by B throughout any statement without changing the truthfulness or falsity of the statement. So example, if I have A to be equal to 4, and then I write A plus 7 is equal to 11, then in place of A, I can write 4, so that I have 4 plus 7 to be equal to 11. And it should not change the truthfulness. So if I write A plus 7 to be equal to 11, then in place of A, I can write 4, because I'm saying that A equal to 4. So I can write 4 plus 7, and this equal to 11. It should not change the truthfulness. Then we have what we call equivalence relation. So a relation R on a set S is called an equivalence on R when R is reflexive. So when you are given a relation and you want to find out if that relation is an equivalent relation, first you have to prove that that relation obeys the reflexive property. You show that it obeys the symmetric property. And then lastly, you show that it obeys the transitive property. So if that relation given obeys these three, then we say that it is an equivalence relation. So the three properties are up here. If the relation obeys these three, then it is an equivalence relation. Then the next, we want to look at addition property. So we are done with the equality property. We want to look at addition property. So if I have properties, if I have ABC in R, so please, you see now, I'm writing ABC in R. And so when I write it like this, then your mind should go to what an R is. So it means that my ABC can be whole number, integer, a natural number, it can be a rational number or irrational number. I'm saying that ABC, they are supposed to be in R. So the first property under the addition law is if A and B are in R, then A plus B should be in R. So I'm saying that if A and B are real numbers, then when I add two real numbers, I'm supposed to get a real number. So if I add two real numbers and I get real number, it means that it obeys the closed property. And we know that any real number that we add, we're going to get real number. So it means that then addition is closed under the operation defined. So you remember closure. And then commutative property says that A plus B is the same as B plus A. And then the associativity property is also obeyed under addition. Then we have what we call identity. So an identity element, those who did elective maths and they did binary operation, we did all these things, closure and addition. Addition and closure and identity. But this one, we are finding identity elements under addition. So we look at the additive identity and then the multiplicative identity. So please, what we are looking at right now is the additive. When we talk about additive, I'm talking about addition identity. So when we talk about an identity element, we are talking about an element that when you add to another element, you get the same element. So we know that in addition, the only number that when we add to any number, we'll get the number itself is what number?
Zero.
Zero.
Okay, so when I pick A, the number that when I add to A, it gives me A is 0. When I pick B, the number that when I add to B, I get B is 0. So the additive identity element is 0. So there exists, so please, when you see this symbol, we call it there exists. So there exists one and only one number, A, such that A plus Z is in 4. So 4, this is 4. That A plus Z is equal to A. This is 4 for A in R. So that number Z, I'm calling 0. So define Z to be equal to 0, and we call it the additive identity. So that number that when we add to any number, we get the number itself is the additive identity. Then what about the multiplication? The number that when I multiply with any number, I get the number itself is what?
1.
So this means that my multiplicative identity is 1. We'll get there. You have it there. Then we have what we call inverse. The inverse of a number is the number that when I add, we are talking about addition. The number that when I add to another number, I get my inverse. I get that one. I have a number A. What number should I get to add to A so that I get 0?
Negative A.
That number.
negative of that number. So if I have a plus a prime is as negative. So my please excuse me, let me read this number. This call, sorry. Hello. Yes. Okay, so sorry. Jacob, your hand is up.
Yes, Doc. Yes, Doc. I was seeing some unusual E sign symbol on the A, which has been turned the other way around. I want to find out if they are mathematical symbols or it's what it was a typographical
Unusual.
the E which is facing the other direction.
I said we call it there exists. There exists. There exists. And then you have some A that has been turned. The A that has been turned, we call it for all or for A in R or for all A in R.
Okay.
So you can write them down so that you don't write plenty. So there exists one and only one number A is equal to A plus Z for A in R, for A in real number, or for A being a real number. Okay. So now we know that the additive identity. Additive identity is 0, and then the additive inverse of A is negative A. So if A is equal to B, then A plus B is equal to B plus C. Okay, so we are talking about cancellation. So this is cancellation. If I have A plus B, and then I can write it as A plus C is equal to B plus C. So that's the cancellation. So these are properties under the addition. So that is the addition properties. Then the next, we want to move on to multiplicative properties. And that one, it says that for all A, B, C, R, first one, if I pick any two real numbers and then I multiply them, I'm going to get real number. So that is the closure. And then the commutative, A times B is the same as B times A. So the commutative operation and the multiplication. Then the associativity, if I have A into brackets B dot C, the same as A dot B in the close the bracket times C. So you can choose any number and you see that it will work. And then we also have what we call distributive property. And we are saying that multiplication is distributive over addition, because I have A outside B plus C is the same as A times B plus A times C. But note that addition is not distributive over multiplication. Multiplication is a distributive over addition, but addition is not distributive over addition, because we have A plus then B times C. This is not equal to A plus B dot A plus C. So addition is not distributive over multiplication. So I just talked about identity. I said that the number that, so the addition, we are talking about a number that when we add to a number, we get the number itself. The multiplication, we are talking about a number that when you multiply by the number, you get the number itself. So if I have a number A, that number that when I multiply with A, I'm going to get A itself is 1. So the multiplicative identity is 1. And we just, what would be the inverse? When we talk about the inverse, the number that when I multiply by the number itself, I'm going to get the identity. So what will be the multiplicative inverse of a number? So if I have a number A, what will be the multiplicative inverse of a number A?
1 over A.
1 over A.
Okay, so for a non-zero number A in R, there exists a unique number 1 over a such that a times 1 over a should give me -1. So AU is equal to 1. It means that U is the multiplicative inverse of A. And we write mu as 1 over A. Okay, or you write it as a to the power -1. So you have, if I have 3, the multiplicative inverse is 1 over 3. The multiplicative inverse of 7 is 1 over 7. Then we also have the cancellation law. If I have A dot B is equal to A dot C, then I can cancel out A to get B is equal to C. Okay, so that is all about the multiplicative property. We also have what we call zero multiplication theory. Zero multiplication theory. And it says that for A in R, A dot 0 is equal to 0. Is equal to 0 dot A. And this is equal to 0. Okay. So it says that when I multiply any number by 0, it's the same as multiplying 0 by that number, and I'm supposed to get 0. So I want to look at the proof. So the proof, I will use the two numbers A and B. So I have A dot B to be equal to A dot B. So the right hand side is equal to the left hand side. So I'll have A dot B, and this is equal to, I know that A dot B, I can write it as A into brackets B plus 0. B plus 0. Do you agree? That A into brackets A,
Yes,
B plus 0 is
Yes, madam.
so when I open the bracket, I'm going to get AB plus A times 0. Now AB on the left and then AB on the right. So I can bring the AB on the left to come here. So I have A dot B minus A dot B is equal to 0. And we know that A dot B minus A dot B is equal to 0. So I have A dot 0 is equal to 0. And that is the proof of the zero multiplication theory. So I have A dot B is equal to 0. Then we have the zero product theory. So I can ask you to state and prove the two. So the zero product theory says that if A dot B is equal to 0, then either A is 0 or B is 0, or possibly both. So if I have the product of two numbers giving me 0, then either one is 0 or both of them are 0. So we'll look at the points. So we are looking at the proof. The point where A is not 0. So I have A dot B equal to 0. If my A is not 0, then it means that I can find the inverse of A. So the inverse of A is 1 over A. So I multiply both sides by A, 1 over A. So this side, my A can go with A. So I have 1 dot B is equal to, and then from the zero multiplication property theory, I know that a number times 0 is 0. So I have 0 here. And then I know that 1 times a number is B, so B is equal to 0. So if my A is not 0 and the product of A and B are 0, then I can prove that my B is 0. If my A is not 0 and then the product of A and B is 0, and I've been able to prove that my B is 0. The other part is when B is not 0. If my B is not 0, and then the product of A and B is 0, I want to prove that then B is 0. So B is not, then A is 0. So if I know that my B is not 0. So if B is not 0, I can find the inverse. The inverse is 1 over B. So I multiply.
Hello, madam, please, your line is breaking. Oh.
Hello, madam. I can't hear anything.
Madam, please, your line is breaking.
Now it's being turned off.
Someone should call.
Hello.
Oh.
Yeah. Adam.
Hello. Yes.
Hello.
Hello.
Madam, we can hear you now.
So the connection has come. Okay, thank you. If B is not 0 and then A times B is 0, then it means that my A is 0. Okay, so that is. Then there's another property. It says that if A is greater than B, A and B are both 0.
Then please, you are
If
not sharing
A
your
is greater than B, and if A and B are both 0.
Yeah, good.
Are you sure? I don't know.
It is.
Oh, it's good. Yes, yes.
Now.
Can you see?
Yes.
If A is greater than 0, and A and B are is less than 1, you can choose any number, 10 and 2. Then
The board is up.
will be less than 1/2. You can look
Your
at
screen is also in place.
Please check
Please,
your
can you see?
network.
Your check also.
From your side, though, we
This is not about network. This is not about network.
Oh, calm down. Here
Please,
we
the
can
slide
see
you are using is not showing.
Network.
Cool. It has come.
Can you see now?
Yes.
Hello.
Madam, we can see.
Yes.
It's okay. Hi.
Yes, Madam, we can see now.
What you can see?
You have a -1 multiplication property.
You can vary
You have
again.
-1 multiplication property that A times negative is a negative, which is -A. Then we have -A times negative A is equal to A. And -A is equal to
It's not showing
A
again.
and A dot B. Any question before we move on to?
Madam, please, your screen is gone again. Immediately start talking.
This thing, it will be from your side, though, because here it's okay.
No.
I can see.
Yeah, it's not showing.
No,
It's
we
not
can
showing.
see.
And it's not about network.
He's not the
It's
only
not
one.
showing.
He's not the only one. So why is it from his side? We can also see it.
It's Madam's network.
Oh, I can.
You see, when voice
She
is
has
stable,
left.
the screen leave. And when the screen comes to
She has
voice
left.
is not stable.
See now?
She has left.
See
Maybe
now?
she's trying to connect it.
Can
No,
you see
please.
now?
No,
No,
please.
please.
No, please.
Okay, it's on.
Okay.
Now present.
Up again.
Okay. Are you in?
No.
No, it's not showing.
Hello?
It seems Madam's network is not helping.
Hey, are you sure?
Mine is showing, my people.
Mine too is
Mine
showing.
too.
Mine is not showing.
Is it okay?
Yeah. Ours are not showing. No.
It's like your
It has not
network is
come.
not stable. That's why it's giving us that right now.
Is it okay now?
Yes. Yes, Madam.
Any question before I continue?
Madam, the final part, that was when the network started misbehaving.
Your hand is up.
Yeah, Madam, I was asking if you can explain the final part again. The one we did before the network became something else.
Is it this one?
Yes, Madam.
Oh, negative one multiplication. We are saying that when you multiply negative 1 by a, it's the same as negative 1 by a. And it's the same as negative 1. When you multiply two negative numbers, you are supposed to get a positive number. When you multiply a negative number by a positive number, you are supposed to get a negative number. So the next I want to look at properties of natural numbers. My time on. So the system of natural numbers is a unique subset of real numbers that has the following property. So we are saying that 1 is a natural number. And for n, a small n in the big number, now n, then big set n, that is a natural number. There exists a number called n star, which is also in n. And we call the n star the successor of n. So if I have the successor of n, n star is written as n plus 1. We are saying that n star is not equal to 1. So n star can never be 1. We are talking about numbers that so when I have 2, the successor of 2 is 2 plus 1, which is 3. When I have 10, the successor of 10, which is n star, is 10 plus 1. So that is it. 11, okay. So the successor of 10 star is 10 plus 1, which is 11. Thank you. My small girl corrected me. You didn't correct me. My class 2 girl corrected me when I said that the successor of n of 10, which is 10 star, is 10 plus 1. And I said 10. You
Madam,
didn't tell me it's 11.
About your time. We are complaining about time, so we didn't want to disturb you.
Oh, no, there's no disturbance. Okay, so if m and n are in big N, and m star is equal to n star, then it means that my m is equal to n. So if the successor of m is the same as the successor of n, then it means that my m is equal to n. And we are saying that the natural numbers, they obey the addition and multiplication properties. So you know the addition and multiplication properties: closure, substitution, identity, they obey all of them. Then we want to look at some properties of integer. And integers are positive and negative whole numbers, so including 0. So the integer we can write from negative infinity to negative 1 union, from positive infinity to from 1 to positive infinity, then union 0. So my integer is written as from negative infinity up to 0, then from 1 to positive infinity. Then properties of integers, they obey the addition properties. Then we have what we call divisor or factors. An integer a not equal to 0 is called a divisor or a factor of an integer b, written as a. Please look at this one. This one we call it a divides b. So in any math book, when you see this, it's written like this: a divides b is the same as b over a. So when you see this, a divides b, this a divides b if and only if an integer b such that b is equal to ac. Example, if C is a factor of 12, if 6 is a factor of 12, then I can write it as 6 divides 12, and it can be written as 12 is equal to 6 times 2. So my B, the number that this divides, I can write it as 6 times 2. Then we have what we call prime numbers. So integers that have exactly 2 factors. Yeah, hello.
Why not write it? You said A divides B is the same thing as B over A. So 6 divides 12. Why not just write it 12 divided by 6?
And it's the same as 12 divided by 6, and it's equal to 2. And from the explanation given, we are told that if A divides B, then I can write my B as A times C. So if I have 6 divides 12, I can write it as 12 is equal to 6 times 2. This is the same as 12 over 2 over 6. Are you okay?
Yes.
Okay, let's continue. So prime numbers are numbers that have exactly 2 factors. That is the 1 and the number itself. It's called a prime factor. So this thing here, IFF, is also, we call it if and only if. If and only if its divisors are plus or negative 1 and then plus or negative A. So prime numbers, they can have factors as 1 and negative 1 and plus and negative or the number itself. Then we have composite numbers, natural numbers greater than 1, which are not prime. Okay. Then we have greatest common divisor. So given a number B such that A divides B, and okay, so and A divides C. So this, we call A the common divisor of A and B. So I have 2 numbers, A and C. If my A divides B and then my A divides C, then I'll call it the common divisor of A and C. Are you okay with the common divisor? I have 2 numbers, B and C.
Yes,
if my A can divide B and then my A can divide C, then I call A the common divisor of B and C. When in addition, every common divisor of A and C is also a common divisor of A, then we call A the greatest common divisor or the greatest common factor. And it is written as A is equal to A, C. Okay. A is the highest common factor of A and B. And A is equal to 1 if and only if A is equal to 1 if B and C are relatively prime. So when what you're talking about is if A and B are relatively, if they are prime numbers, then their greatest common or the highest common factor will be 1. So we can also look at rational numbers. So rational numbers are defined by the set denoted by Q, and it is defined as Q such that Q is equal to A over B, and my A and B are in Z. My B cannot be 0. So Q is equal to numbers whose decimal representation terminates or repeats. So I can have, okay. So note that A over B is the same as 1 over B times A, which is the same as A dot 1 over B. So properties of rational numbers obey the properties of addition and then multiplication. It also obeys the cancellation law. Now let A, B, C, D be integers. And let A, B be in not, let B and D not equal to 0. Then A over B is equal to C over D, if and only if AD is equal to BC. I hope you can see that. If I have A over B is equal to C over D, I can rewrite it as A multiplying D and then B multiplying C. And then the proofs, I want to prove that A over B is equal to C over D, if and only if AD is equal to BC. So first I have A over B is equal to C over D. And then from what we saw earlier, A over B can be written as A times 1 over B, and this equal to C times 1 over D. Then I can find the LCM for B and C. A B and D, the LCM for B and D is BD. So I multiply both sides by BD. So I multiply this side, the left hand side by BD, the right hand side by BD. Then my B can cancel B, so I have AD times 1 is equal to BC times 1. And we know that a number times 1 is the number itself. So I have AD is equal to BC. So that is the proof that if AB is equal to BC, then I can get AD is equal to BC. Now for any non-negative number S and any rational number A dot B, A over B, where B is not equal to 0, we have what we call fundamental property of rational numbers. The fundamental property of rational number says that if I have A over B, when I multiply the A over B by X and divide by S, I will get A over B itself. So that is a fundamental property of rational numbers. So A times S over B times S is equal to A over B. Then we come to irrational numbers denoted by Q prime. They are numbers whose decimal representation do not terminate or repeat. And we are saying that number that do not have fractional representation. So example, we can have root 2, root 3, root 6, pi, e, and then we have the number 3.67, whatever. Now the expression root of b, we call it the radical expression, and the b, we call it the radicand. Now if root b is irrational, then a plus c times root b will also be irrational, even though my a, b, c are rational. And then when I multiply a plus c root b by a minus b, a minus c root b, let's see what we're going to get, because what I'm getting here is not convinced. So please let's multiply a. I want us to multiply a plus, what is this? So I have a plus c root b, and I want to multiply it by a minus c root b. Please let's multiply it. So we have this time, this is a squared. Then I have this by this, I have plus ac root b. Then I have this by this, I have, where am I?
Madam, it's supposed to
be minus is.
So it's supposed to be.
Yes, madam.
Okay, thank you. So I have minus. Then I come here. This time this is plus
Plus
a c root b.
B.
Then this time this, which is minus c squared times a times b.
Times b.
Times b.
Yeah.
So this goes with this. Then I'm going to get a squared minus c squared b. So I think that there's a mistake somewhere here. So there's a mistake here. And we can see that this is a rational number. It's a rational number, right? So this will give me a rational number. So what we are saying is when I multiply a rational number by its conjugate. Okay, so when I write a number like this is plus and then this minus. We call this the conjugate. So this is the conjugate of this and this also the conjugate of this. So if I multiply a number, a rational number by its conjugate, I'm supposed to get a rational number. So that's all we want to say. So maybe we have to correct that. The next one, we want to show that the number root 2 is an irrational number. We want to show that root 2 is an irrational number. So to prove, we have different ways of proving. We have proof by contradiction. So contradiction, I want to prove that root 2 is an irrational number, but I will start by saying that it's a rational number. Then I will prove and then conclude that it's not a rational number, but it's an irrational number. So I want to prove by contradiction by assuming that root 2 is a rational number. Now, if root 2 is a rational number, then I should be able to write it as A over B. So we said that rational numbers can be written as fractions. So my root 2, I should be able to write it as A over B, where A and B are integers, and my B is not equal to 0. And then the greatest common factor should be 1. So please remember this. A comma B is equal to 1. This means that my greatest or highest common factor for A and B is 1. So what I've written here, I've written a lot of brofu here by a mathematical way. Root B is equal to A over B. Root 2 is equal to A over B means that this is a rational number. And my A and B is equal to, they are integers. My B is non-zero, it's greater than 0. And then it's not equal to 0. And then the greatest common factor for A and B is 1. That is it. So when I come here, if root 2 is equal to A over B, I can write it as 2 times root 2 is equal to A. Now when I square both sides, I'm going to get 2B squared is equal to A. And then mostly when we write even numbers, we'll write it as 2 times. Yeah, mostly, anytime we write even number, you know that even number is a number that is divisible by 2. So I can write it 2 times something. Now I have 2 times B squared is equal to A squared. This means that my A squared is even. And since my A squared is even, I can say that my A is also even. And I can write my even numbers as 2k. We write even numbers as 2k. So in place of A, I write it as 2k. So this means that my 2b is equal to 2k squared. So I'm going to get 2b squared is equal to 4k squared, which is the same as b squared is equal to 2k squared. And then this also means that my b squared is even, because I can write my b squared as 2k. So my b squared is even implies that my b is even. So if my b is even and then my a is even, then this thing here is not true. My A is even, my B is even. So this means that my greatest common factor cannot be 1. So let's continue. Thus, A and B are both even and have 2 as a factor, which contradicts the earlier assumption that they have a greatest highest factor to be 1. So because we have even contradicted that one, then we can say that our root 2 is not rational. And if it's not rational, then it is irrational. Are you okay? Hello?
Yes, madam. Yes.
Are you okay?
Not all.
Yes,
Yeah. So my A is even, my B is even. Earlier I said that A and B have greatest higher factor of 1. But we've seen that A is even and B is even, and 2 is also a factor. So they cannot have greatest or highest common factor to be 1. So even that one is a contradiction. And since it's contradicts, it means that my root 2 is not rational. It's not a rational number, it's an irrational number. We have what we call axiom of order. So we'll just look at the axiom of orders, then we'll end for today. So given any 2 numbers A, B, and R, one and only one of the following is true. So either A is equal to B. So if I have 2 numbers, either they are equal, or A is greater than 0, or B is less than A 0. So these 3 laws, these 3 combined, we call them the dichotomy's law. Then we have what we call the transitive law. It says that if A is greater than B and B is greater than C, then it means that my A is greater than C. That is the transitive law. If A is equal to A prime and B is equal to B prime, and A is greater than B, then it means that my A prime is greater than B prime. And then if A is greater than B, and K times A is greater than K times B, then it means that my K is greater than 0. If A is greater than B, and then K times A is less than K times B, then it means that my K is less than 0. Please, you can look at them. That's. And the next, I want to show that for any number x not equal to 1, x squared plus 1 is greater than 2 squared. We'll look at that later. Or you can take that one.
Is it 2x or 2 square?
2 squared plus 1 is greater than 2. Then 5 says that A comma B greater. So if I have A and B greater than 0 and then A greater than B, then square root of A minus square root of B all squared is greater than 0. So I can open this. When I open this, I'm going to get A minus 2 root of A B plus B squared greater than 0. So this is true. Square root of A minus square root of B, all squared will always be greater than 0. So when I expand this, I'm going to get A minus 2 root of AB plus B greater than 0. Then I can write it as A plus B greater than 2A. Then I divide through by 2. I'm going to get A over B, A plus B over 2 greater than root AB. And we call A plus B over 2 the arithmetic mean. And we call root of AB the geometric mean. So what we have here, we call it the arithmetic mean geometric mean inequality. I have 3 minutes. Absolute, the real number system is the number line is a topic on itself. So I am done with the real numbers, their properties, and everything. I want us to end here so that when we meet next time, we'll look at this and then we'll see what we can do again. But I have 2 minutes. If you have any question, you can ask. Then we use the next 1 minute for our break.
Madam. Around this latter part, you have used us to run.
Oh, please, you can just read the note. It's not difficult. Yes, Isa.
Hello, madam.
Yeah.
Madam, I want to beg and see if I just want to beg. This is just a suggestion so that we can get some sample questions with regards to this. Those that we just went through, likely possible questions from
Okay,
the first.
don't worry, don't worry. Thank you, Isa. Don't worry. Let me catch the written. Please, I will try and see if I can get questions, but I think AI should be able to help you too. So maybe you can give AI what you want, maybe some likely questions on the topics, and AI should be able to help. But I also try. Yeah, I cannot promise you because I'm a Dibronya. I have to enjoy. So I'll know I cannot promise you, but I'll try and see if I can get some questions for you.
Oh, madam, please.
Please, madam, we need a slide for today's lesson.
Didn't I give the slide to you last time? It's the same thing.
It's the same thing in our group. The same thing.
So it's the same thing. I think we have to do that.
It is combined.
Madam, please, though we those in ICT, we aren't in the group, and they have not added us yet, so we haven't gotten any.
You can contact me and you get the notes.
All right.
All right, madam. Thank you.
Mr. Chairman, your hand is up. Al-Hassan first. Al-Hassan first before chairman.
Yeah, madam. Like the question that he was asking, like, we want to know how the question is framed when you are to do the exams or something like that. How they frame the question in respective with.
So you look for past questions, Al-Hassan. You look for past questions. And the questions they come as the Spirit leads me. So
Merry Christmas.
Hey, madam.
Come on,
Madam, Merry Christmas.
Just set one example and give it to us. We are okay with that one.
I'll look for questions and give it to you. Don't worry. I will try. And get
Hello,
madam.
Hello, madam.
Yeah, Foster. Is it Foster?
There's Salom.
Okay.
Those of us.
Hey, Salom is off. He's talking.
Okay, madam.
Hello, hello.
Yeah, please.
Yeah, we always
excellent.
struggle to get to the right class to join. We were this morning too. The same thing happened as last week. The link that we supposed to, we joined and it was different class altogether. So we wasted time before realizing that we're supposed to join this particular one. In fact, it's disturbing us.
So you don't have your timetable, Salom.
We have the
timetable. Know your timetable.
No, we have the timetable. And what?
And you don't know your link, Salom.
Madam, what I'm saying, all of us from the ICT class know what I'm talking about. The link that we're supposed to. Yeah.
Hello, madam.
So please let's do our assignment well. Let's look for the right link to join at each point in time. So please, ICT people, please try and get your course rep. I don't know your course rep. Then the course rep, Saturday is 7 o'clock in the morning.
Unfortunately,
7 o'clock a.m. is for algebra.
Madam, I have a question. Madam, I have a
question.
Let's
allow chairman to speak first there because chairman and the paying him.
Madam, please, I wanted to know, please, I believe you are the coordinator for this course.
Chairman, what is it? You want to do what?
I said I wanted to know whether you are the coordinator for this course too.
Chairman, you didn't read your timetable. It's on the timetable. The coordinator's name is on the timetable. Chairman.
Thank you, madam.
Why do you want to know if I'm the coordinator?
Madam, you that one will reserve it.
So chairman, look for the timetable and see who the coordinator is. Sir Dominic, your hand is up. Dominic Aka.
Madam, please, I wanted to ask a question. Where you started from the axiom?
Okay. Ask.
Is it? On the screen, it was A equals B, A greater than B, A less than B. But I heard you saying A less than 0, A greater than 0. And when we were moving across, 0 came in.
So it is A equals to B, A greater than B, or A less than B. These are the trichotomy's law.
Okay. Thank you, madam.
You're welcome. That's all. So I want to give you 15 minutes. I want to give you 15 minutes break from my time. John A, do you want to say something? Mr. John A.
Well, yeah, what I wanted to say was what Salom was saying. I just wanted to chip in something small. The thing is, when it comes to the math IT class, though they have the timetable and the link or everything intact, but the truth of the matter is that when you join that particular link where they have the word school together with the one in charge, when you join, you will not see anybody there, you will not see the lecturer there. So this morning, when they place it on,
are you supposed to join that group?
No, yes. They were supposed to join the online group and not the West Coast.
So look for my link.
Hello?
Hey, yes, Mr. John. Edu.
So you will join the lecturer will not be around. So I think this morning the course rep had to contact the coordinator on that issue. And then he said that the lecturer has swapped with another teacher, of which tomorrow to that particular class, I mean the IT mathematics, they'll be having 2 lessons tomorrow. So if they swap it, that means they are going to have 3 classes tomorrow, and it will be classing with each other.
But so are you supposed to join mine? Are you supposed to join mine, or you are supposed to join his?
Actually, if you are going by the timetable, you are supposed to join. Yeah, if you are to look at the timetable, you are supposed to join the West School link. But when you join, nobody is there.
Were you not there when they were taking that decision? Were you not there when they were taking that decision?
On the estimate
to swap. Yeah.
No, please. That one they did not inform.
No, madam.
No, madam, they did not inform
so
any of us.
No communication comes. You just join and realize.
So you have to contact your colleagues, because for the swapping, the lecturer can decide. The most important thing is for the lecturer to teach. So if the lecturer is busy, he can discuss it with the coordinator and then maybe fix another time. So you have to contact the lecturer or the course rep to know the time that they've shifted the class to. But if it is algebra and trig, and you want to join my group, no problem. You can be here. We are doing the same thing. We are teaching the same thing.
Sure.
Madam, we are
So
here
if you're
already.
okay.
Sure. Thank you, madam.
You're welcome. But you go and tell the lecturer that he should give me part of his money because I'm teaching you.
Madam, the lecturer, we have been calling him, but he's not answering our call. We had even wanted to inform him that if it will not be possible for Saturdays, he should let's schedule to maybe some of the weekdays in the evening, then we meet. But he's not answering our call. So it was just this morning that the course rep contacted the one who is in charge of the timetable and the rest, the coordinator, and then he was giving us something like some sort of, it would be like we will find time and then fix that So
Okay.
that is,
Okay.
and because now we have missed 2 lessons, 2 classes. Last week we couldn't
Wow.
join. So today too, so making it 2, and we don't know what will
So
happen from.
I'll look for that lecturer and then discuss, find out what is happening with the
All right.
class, and then when we meet next time.
All right, thank you, madam. We'll be
You're
very,
welcome.
very happy. And we enjoy your
Yes.
lesson.
Hello, madam.
I hear. Yes, sir. Thank you. Sir Oliver.
Please, madam, are we still, will we be still meeting us after the break?
Yes, so
Because
we are supposed to
because
close.
we have another
We are supposed to
hour.
close at 11.
Yes, madam.
Close at 11.
But
Yes,
it's,
madam.
it's already 11.
Madam, we have
Our next lesson is 11:15. Our next lesson is 11:15.
I'm done.
So, madam, we are proceeding to
Yes, madam.
Done for the day. So sir, first.
Okay, madam.
Yes, sir. First
Okay,
of anything
madam,
for
I
us.
wanted to talk about the issue of we mixing our lecture. I think last week we joined the same lectures. Then you confirmed that we should be joining this one, the online one. So we should use the first
I
link
thought
in the
you were.
time
I know. I didn't confirm. I thought no. First, please. I didn't confirm. I thought you were.
First,
I thought you were my student. That's why I said you should join.
It was analytical. First, even
No,
what
this
she was saying was
same. Even Madam did not finish. She said that she is not
Don't
all
worry,
that
I'm here for my
healthy.
students, and I don't know my students. My students are supposed to come. So if you think that you're my student, you can be here. If you are not my student, you go and look for your lecturer.
Madam, you are a lecturer.
I hear. Thank you very
Please,
much.
We are already at UCC. We are coming for our Christmas gift. I believe that.
No problem. No problem. I'm here. You just dress well and then wear your Christmas hats, Christmas shoe, everything. I'll give you your.
All right.
Okay. Thank you very much, and then Merry Christmas to